everybody's here. So we can get started. So we have 3 talks this morning. We do have the room for 2 hours. So you can use 40 minutes if you want, depending on how many questions there are. Okay, so we'll get started with the first speaker. So, Anastasia.
So, hello everyone, I'm Anastasia. Hopefully everyone knows that by now. So I'm from Edinburgh, from the MacMix CDT Center for Doctoral Training. I work with Aretha, who is one of the organizers of this DDE program. And we work on smoothing and with applications in multi-level Monte Carlo method. Okay, so as an outline for the talk, I will start with an application that sort of motivates the work that we've been doing for the past year. I will talk about circulant embedding methods and multi-level Monte Carlo methods, and then how we combine them in our numerical experiments, and conclude with some remarks and potential avenues for future work. And the point of this ugly diagram really on the slide is not to show my design skills, because I don't have any. But it's to show that the goal of this project is really to get computational speed up. So we're combining this circulant embedding method with something that we call smoothing and multi-level Monte Carlo methods to essentially develop faster algorithms. Okay, so what is the application that we focus on? This PDE here, it essentially models the subsurface, the groundwater flow. So that is a steady state, single phase subsurface flow. Steady state means that the properties of the flow at a given point in the domain do not change over time. Single phase means that we just have one matter essentially. So just liquid or just vapor or whatever, but here we focus on liquid, versus multi-phase where we would have multiple flows with 2 or more different thermodynamic properties. So the PDE on the slide, in the PDE, here is the solution, the pressure of the fluid. F represents the source terms, and K is what we call the hydraulic conductivity. That tells us how easily the water flows through the Earth's subsurface. So, as you can imagine, or as this picture is meant to illustrate, if we take a horizontal cross surface of this cross-section of this domain, at every point in the domain, the hydraulic conductivity will change. It is not constant. That is because we have different rock structures under the subsurface. And because we don't know what it is exactly, we also put some randomness in it. So K there depends on X and omega. So it is what we call a random field in our case, a 2-dimensional Gaussian process. So K is to the final number of D times omega, where omega is our sample space, and the probability space with 1 in 1. So that means that for fixed point in our domain D, K is a random variable, whereas for a fixed omega, K is just a deterministic function. Okay. Stop me at any point if you have any questions, because I don't really want to talk to myself for 40 minutes. Okay. Yes. Okay, so for the boundary conditions, we impose mixed boundary conditions. So that is Dirichlet and Neumann boundary conditions. So the Dirichlet boundary conditions on the vertical axis, they ensure that the flow is from left to right in our domain, whereas the Neumann boundary conditions, they ensure that the flow does not leave the domain vertically. So it's what we call a self-flow boundary condition. Right. And In this problem, we're specifically interested in uncertainty quantification, specifically the forward problem. So that means that we impose some covariance, some probability law on our random field K. And then we want to say something about the output of the PD, about the pressure P. This is different from the inverse problem when we have measurements on the solution, on the pressure P, and we want to say something about K. But actually, and when we solve the inverse problem, we actually have to first solve the forward problem. So this is where the forward problem comes in. Or if we have solved our inverse problem and we just want to evaluate the model, we have to solve the forward problem. And there's usually two ways of doing this. We have sampling and non-sampling methods. The non-sampling methods are based on the variation of permutation, where we expand K in the form of a series, well, a truncated series, in some bases, and then we expand U in some, for example, polynomial bases, and we end up with a huge linear system that we then have to solve. But we don't do that here. We use a sampling-based. So in the sampling-based method, we assume that we take one sample K, views into 2D, for example. For this sample K, because omega is now fixed, this is just a deterministic function. So our PD becomes just a deterministic elliptic PD. So we can obtain an approximation of our solution U. Using our favorite numerical solver, but we just use finite elements here with linear polynomials. And this then gives us an approximation of what we call the choose here the function of the solution U. This is going to be approximately G. So this is just for one sample of K. Q here can be, for example, the point evaluation of the solution, or it can be a norm or any functional, any bounded functional. But then we have to find a way to post-process all these samples that we have taken. And so we'll see how we do that in a minute. First, we have to see how we actually sample from our random field. So first, we impose some assumptions. We assume that K is a log normal random field, and that is because so that it means that K is the exponential of a Gaussian field. That is because that makes K positive, which is both for positiveness, but also for physical meaning, because as I said, K in our applications models the hydraulic conductivity, which means that it has to be positive. And then for Z, we impose a zero mean structure, and also for the covariance function. So this, we impose the assumption that the covariance function is stationary, and this is actually quite important for the circulant embedding method. So the fact that it's stationary means that the covariance function is just a function of the difference of the 2 points in the domain. So the only thing that matters is how far apart the 2 points in the domain are, not actually where they are. And a while ago, someone has looked at some measurements from this pressure of the water somewhere in New Mexico, I think, and they've come up with the following covariance structure for the random field. So this is just an exponential covariance with two hyperparameters. Sigma squared here is the variance, and rho is what we call the correlation length. But in our numerical experiments, we've used the Matern covariance as well, if you're familiar with that. So how do these hyperparameters influence the samples from the random field? So let's look at the variance first. On the left here, the correlation length is fixed, but the variance is 1. And on the right, the variance is 10. So we can see that these two samples essentially look the same, but the z-axis is different. So the variance doesn't actually matter that much. The important parameter is the correlation length, because as the name suggests, that this controls the 2 points at which the 2 points in the domain at which the samples tend to become uncorrelated. So on the right here, we use a correlation length of 0.1, so that is quite small, and we can see that is quite oscillatory. And this is usually what we're interested in practice, in this small correlation lengths.
Did you have problems where the source down is random as well?
Yeah. So I mean, here we use a deterministic one, but you could equally make it random.
Will it be what you're going to present be quite generalizable to that?
Yeah, you can do Monte Carlo on that as well. Any other questions? No, okay. So so how do we actually sample from this random field? So we aim to use circulant embedding, which is a factorization based method. But there's one observation that is important here. So in the PDE, K here is a constant function. Sorry, it's not constant, it's continuous. But these factorization methods that I'll talk about in a minute, they are inherently discrete. So they usually start with a mesh. And if you just think about it in 1D, we have one interval from say 0 to 1, but it doesn't matter, with some discretization points. And the result of this method is essentially a vector, let's call it Z, that gives us the value of the random field at each of these points. So it is not continuous, it is discrete, which can create problems. So from this discretization mesh, what we do is we construct a covariance matrix, so that each entry in the covariance matrix essentially has this form. But as we have said, this is going to be the value of the covariance function at xi of j. This is stationary, so this is going to be xi minus xj. But because we're in the interval 0, 1, these are just points of the form I over m, j over m. So this is just I minus j over m. So this is how we construct the covariance matrix. Any questions? And then under the assumption that we can factorize this matrix in this form, we can take a sample from the standard normal distribution. And then this will then give us a sample, the discrete sample set from the random field. I think that is all I wanted to say. I think so. So we can do this using, for example, a Cholesky factorization. But these are usually quite expensive. They have complexity of order n cubed, where n is the size of the matrix. So this is where the circulant embedding comes in. Because in circulant embedding, we don't factorize the covariance matrix directly. So we start, as I said, from the discretization mesh. We construct the covariance matrix. We then embed this matrix in a circulant matrix S, and I'll explain how we do that in a minute. But the cool thing about circulant matrices is that we can factorize them using the fast Fourier transform. But the Fourier transform gives us a factorization of the form where F is the n-dimensional Fourier matrix, and F star is the conjugate transpose of F. But we can actually show that we can replace F by the real plus the imaginary part. So that is G there on the slide. And under the assumption that the eigenvalues are real and positive, so that is that the embedding matrix is symmetric, positive, definite, we are in the setting that we had before. So that is a factorization of the form theta, theta transpose. So we can take a sample from the standard normal distribution, and that gives us a sample from Z, a discrete sample. Right, so how do we obtain the circulant embedding matrix? Well, as I said, so we have in the matrix R, we have entries of this form. And the additional assumption that we need for the circuit for this method to work is that the mesh that we started with is uniform. So that means that, for example, in this case, if we look at the first upper diagonal in this matrix, so that will be it, but I mean, it's not here. But on that upper diagonal, all entries will be of the form xj plus 1. So all these points will be essentially 1 point apart. So that diagonal is constant. And if you look to the second upper diagonal, those will be points of the form xj plus 2. So that will be C2. And this matrix is symmetric because it is a covariance matrix. And so we get a Toeplitz matrix essentially because all these diagonals are constant. And that is what makes circulant embedding works, because then we can take our covariance matrix R, we can mirror it column-wise. So we take the second to last column and essentially move it to the right. And we repeat this process until the second column. So we ignore the first column. We then do the same process, but we mirror it row-wise. And then for the last block, we mirror it row-wise and column-wise. So now this is a circulant matrix, which means that every row or every column in this matrix is a circulant permutation of the first row or the first column. So circulant permutation, for example, if you look at the second row, is where we move, essentially, we shift every element to the right by one element. So that is why when we compute here it's not a formal proof, but as an intuition, when we compute here the eigenvalues, we can take the Fourier transform of the first row or the first column of the circulant embedding matrix. As it says. Okay. So that's how we get the eigenvalues as well. Right. Any questions so far? Okay. So as I said, we in order to take this factorization here, we have to make sure that the eigenvalues are real and positive. And we can show that for the covariance matrix that I showed earlier, the P-norm covariance, the eigenvalues are actually, we can prove that they are real and positive. So we don't have to worry about it. But for the Matern case, that is not always the case. We get real eigenvalues because the embedding matrix is symmetric, but it is not always the case that they are positive. So what we can do in that case, we can show that as the covariance matrix becomes larger and larger, we are guaranteed to obtain positive eigenvalues. So then we extend the covariance matrix, which means that we just artificially add some more. So we have all the inputs that we bought before from 0 to m, and we just add some more value. Where j here, we call it the padding parameter. And these values we obtain by essentially periodically extending the covariance function that we started with. But I will not talk too much about that because actually in practice, in the cases that we're interested in, that is the small correlation length cases, we don't need this periodization. But it's useful for the theory.
So you're also talking now only about the one case, I guess.
Yeah, you can easily extend this to multiple dimensions.
Yeah, okay.
Sorry? Yeah, you get, yeah. So in 2D, well, in multiple dimensions, you get a block Toeplitz matrix. with topless blocks, and then circular matrices will be circulant with circular blocks. Yeah.
Do you require the xi to be equally spaced?
Yeah. So that is, I think you can extend it to non-uniform meshes as well, but in our cases, we use uniform meshes. I mean, so I'm not entirely sure how you do that, but I think I have a reference somewhere.
You can, depends what you're trying to do with it.
Exactly. Yeah.
Solve that.
Sorry, you're saying what you do to get the eigenvalues positive?
So what we do is we extend the covariance matrix. So, oh, sorry. So before we had this covariance matrix, and now we just, as I said, we artificially add some values. So we add some more rows and some more columns, because we can show that as the dimension of this matrix goes to infinity, essentially, that we are guaranteed to get positive eigenvalues. And we can also obtain a theoretical bound on how much we need to extend this covariance function or covariance matrix periodically to get positive eigenvalues.
And how do you get the new values? By adding to them, like by making the mesh wider, or?
So before we had a covariance function. So we have let me see if I can describe it. So if your covariance function is defined on the domain minus LL, I mean that you're extending it to the periodic domain minus LL from your original domain. And here's in ZD, and then phi k here. So C is your original covariance function, and phi k is what we call a cutoff function. So it can be, for example, just the characteristic function. So if your covariance function looks something like this, you just extend this, and then your additional values will be evaluated on the periodic extension. So here Cm plus 1, it will be of the form n plus 1 divided by n, which is outside the domain minus 1, 1 that we originally worked with, but we can get the periodic extension and evaluate it outside the domain.
Thank you.
Does that make sense now?
Yeah. And there's no need to add diagonal epsilon or.
No, you don't have to. But I think there's someone else in the audience who knows more about periodization-based methods than I do. Okay. Okay, if there aren't any more questions, I'll move on. So now that we know, quite easily how to sample from the random field, we have to think about how we post-process all these samples. And the simplest thing we can do is to take a Monte Carlo average. So that just means we just take lots and lots of samples on just one mesh with a single grid resolution, and we just average them to compute the expected value of this quantity of interest. And so we can show, if we look at the mean squared error, if you look at the mean squared error between the Monte Carlo estimator and the true quantity of input that we want to estimate. So this is the true quantity of interest that we're looking to estimate, and we call this mean squared error. And we can show that it's going to be equal to. So we essentially get the variance bias decomposition. So this is the variance, and this is the bias or the discretization error. And if we want to impose a certain accuracy, for example, epsilon squared on the mean squared error, we have to ensure that both the variance, we have to balance the variance and the bias. So that usually means that we get a very large number of samples with a very small discretization parameter, so a very fine mesh. Which means that the computational cost of these methods usually grows very quickly. And this is where multi-level Monte Carlo comes in. So in multi-level Monte Carlo, we essentially avoid estimating the quantity of interest directly on this finest mesh that we had before in Monte Carlo. I mean that. So the formula on the slide is a bit confusing, but it's essentially saying that if N is our finest mesh, then we write it with a telescopic point. So this is now a telescopic sum, where, as you can see, all the terms will cancel apart from the very last one. And what the formula on the slide is saying is just that we're taking Monte Carlo's averages of those expectations in the telescopic sum. So this is usually more computationally efficient because we assume that as we refine the mesh more and more, these discretizations get closer and closer to each other. So the QL and QL-1 get closer and closer together, which means that we will need less and less samples on these finer levels. So we're clustering most of the computational effort on the coarsest mesh, where it's very cheap to compute samples. And then we refine the mesh and take differences to essentially correct this original approximation that we had. And then if we look again at the mean squared error, we will get something very similar, but the only difference is going to be the variance. So instead of this variance, we'll have as you might expect, the variance, the sum of the variances on each level. So that's why we get smaller, we get less and less samples on each level. Okay. Any questions?
How many different Ks do you sample now?
So the case depends on NL, where NL is the number of sample. So for each sample, we have to, for each sample of this quantity of interest, you have to sample from K. You need to have a different sample from the random coefficient.
But you do refine the same K all the time or not?
So if you're on level, say if you're on the second mesh there, then you construct your coefficient on that mesh. And then for the coarser level, which would be the other grid, because these grids are nested, you can just take a subsample of the sample on this grid, right? Because, I mean, this point corresponds to this point here, and this point corresponds to that point here. So you essentially have the value of the random field at those points already. So you just take a subsample for the coarse mesh, because in the difference, in the levels, you have to use the same sample from the underlying sample of the random coefficient.
So you basically take very few on the very fine level, and the part where it gets one sample of A will make on that level, or is it the same or not?
Yeah, so you take very few samples on the fine levels, but by a level we mean a difference. So you essentially have QL and QL-1 on one level. So one level means this.
You don't even need to do all the oddities to have it one different. Okay. Okay, yeah. Okay, that's very good. Okay. Thanks.
No worries. Any other questions? Okay, so even with the multi-level Monte Carlo estimator in this regime of very small correlation lengths, we can get extremely oscillatory random fields on which the coarsest mesh we can use, so the Q0 here, has to still be resolved on a relatively fine mesh. And then if you still have a fine mesh for the coarse mesh, the number of levels that you can then subsequently use is limited. And therefore the computational gains that you can get from multi-level Monte Carlo is limited. So what we proposed was to still use this coarse meshes, but with approximations of the random field on them. So rather than using the full realization, we use a smooth approximation, and we obtain the smooth approximation by dropping some eigenvalues in the factorization of the embedding matrix. And the number of eigenvalues we drop depends on the error we want to introduce. So we can show that this is the error we obtain, where Z tilde is the smooth sample now. S is essentially the dimension of the embedding matrix, and K is the number of eigenvalues we drop. And the lambda J's are the eigenvalues. So the most important factor actually in this bound is the decay rate of the eigenvalues. And we can show for the p-norm covariance, we can show that the decay rate of the eigenvalues is this form, and then for the different case, it's this one. So once we have the decay rate for the eigenvalues, and we know the error that we want to impose on the smoothing, then we can compute the number of eigenvalues we drop in the smoothing.
So you do the smoothing, but what eigenvalues?
Yeah. Yeah. So that is because we know that the smallest eigenvalues correspond to the highest oscillations here. So if you just remove the smallest ones, then this is what you're left with.
If I drop eigenvalue, I'm guessing you don't set them to 0.
Yeah, you just set them to 0.
0.
Yeah. Because so G there is I didn't write it down, but it is the real part plus the imaginary part of the Fourier matrix, which is essentially just Fourier modes. So when you set the eigenvalues to 0, some entries in your Fourier matrix, when you multiply them together, will also, in the resulting sample, will also be 0. That makes sense, right? Because this is a matrix, it's a diagonal matrix of eigenvalues.
But for this graphic, you use, you're showing two, this is the random field, right, with different eigenvalues. But this is using presumably a fine mesh.
Not very fine. I mean, it depends on what you mean by
Fine
fine.
enough to resolve.
On the left, I mean, yeah, on the right is the same mesh as well, yeah.
So have you used the mesh, coarser mesh, which we would be using anyway with the K of that, or with the dropping the eigenvalues. But the picture was different.
Would the picture look different? I mean, it would probably look different, yes.
But I mean, in the sense that you have the high frequencies there,
Yeah.
which are visible, but because you are resolving the image, and you had a coarser image, you wouldn't even see those.
Yeah, you wouldn't see this many oscillations, but you would still see high oscillations. you would still see this, you know, close enough oscillations, but just on a coarser mesh.
So that is exactly the problem, but if you take the field like a left-hand side, and you just on a post rate, if you then use that in terms of the multi-level Monte Carlo, then think of refining the grain, that difference is going to be large. And that's the problem, that then the variance in the difference is not small, because you have all of these fine scale oscillations that you go from a coarse grade to a fine grade. You are adding so much information because on the finer grade you are able to resolve more of the high frequencies. That's exactly the issue, that the variance is then not small.
But presumably you're doing that anyway. That's what you're doing. You're adding those kind of frequencies when you go from the coarse mesh to a fine mesh. You know, so from one level to the other, you're not adding more frequency.
Yeah.
In what way? I mean, if you maybe discuss
Yeah.
You're sure that it's the same sample, but essentially you do the same random vector.
Mhm.
You truncate the
Yeah, this is using the same site. Yeah, it's just the lambdas that are
that way you ensure the vector is
exactly.
Not cutting things taking time within the power of from that so that it goes to zero quicker. If you want to just like using some kind of here you are using some kind of SDG where you just drop out. You could also decrease them to not something that remains smooth like what we can do in smaller spaces. With the people that do that, or in practice, there is no need, and just getting in some end value and dropping down everything.
I think this, I mean, I don't know of anyone who does that.
You can change the speed from the correlation structure.
Yeah.
So it would actually be the same. But yeah, this here is the same. If this, like, wouldn't the natural thing be to use a K that corresponds to a well-defined infinite dimensional limit? Because then it can't be that you're always adding more information that keeps that in the K very rapidly, right?
Right, but then you still have to, so do you mean just take like a K on a very fine mesh and then?
Yeah, I mean, if you take a K that corresponds to one that will then be in L2 or in some sort of abstract or something, then this shouldn't, I mean, this looks as if the infinite dimension would not be well defined, right?
No,
But this looks like it would converge to.
I think the correlation is not what for this quite small, but it is perfectly well defined.
But if you want this, why don't you just then take, for example, or equal to 0.5 or something?
Oh, that's just me forgetting to relate back to applications. So that's because in practice, if you're looking at like very large domains, that even if you look at large correlation lengths compared to the size of your domain, that's still a small correlation length. And that's usually what you're interested in practice, and this small correlation length regimes.
Well, but I think that this question was more why the smooth by choosing a larger correlation length in the smooth picture. So what you ask?
No, that we, but maybe.
But you could also do that. You could also do that.
Expensive.
Yeah.
No, I mean, I think what I'm more asking if you want, are you doing this at every, so the finer you get, the more eigenvalues you will drop, so that it always still keep it function?
Yeah, so the smoothing, so there's two ways you can do the smoothing. You can either essentially smooth all the levels up until the finest one, but on the very finest level, the last term that's left in the multi-level Monte Carlo telescopic sum, you have to use a full realization of the random field. So you cannot introduce an approximation there.
Okay.
So because in the telescopic sum, all the terms will cancel, you can, more or less do whatever you want on those levels up to a limit, of course. But you can also just find like the levels that need the smoothing, apply the smoothing on those levels, and then just leave the other ones untouched.
So this very rough thing does go into some of the new ages on the high level. You know.
Yeah, so.
Okay, then yeah.
Okay. Someone else had a question? Oh, okay. So, yes, I'm done. Just to show that in the numerics, we don't actually need a smoothing for still relatively large correlation lengths. So I'll just skip this for brevity, but for small correlation lengths, we are in this regime where so the blue line here corresponds to the Monte Carlo computational complexity, and the red line corresponds to the standard multi-level Monte Carlo. So you can see that here Monte Carlo actually performs better than multi-level Monte Carlo, which is obviously not what you want. That's not the point of using multi-level Monte Carlo. But once you introduce the smoothing, we are back in the this actually performs better than Monte Carlo. And I mean, the point where these two lines cross is will essentially move further to the left once you have even smaller correlation lengths. Yeah. The exponential. Yeah, so you can't compute the mean squared error. I mean, actually you can, under some assumptions. So. This. Write this. And then if we're really relative expectation, we can do this out. And then under the assumption that this expected value decays at some rate, then you can replace this by H L to the alpha.
You say like a very defined grid, and then
Well,
you
you take consecutive grades here essentially, so you can do it on every level as long as you have the both HL, QHL activation.
still with the truncated, I can tell you.
Yeah, you can do it with the truncated eigenvalues as well in a similar way, but then here you have Q tilde corresponding to the smooth sample, and under a similar assumption, and assuming you cannot compute this, it's not an assumption, you cannot compute this, you'll just get a different constant.
Same quotation. Has something this picture or?
The truncation depends on the accuracy. So it's not going to be the same one because it depends on epsilon. But we use, as I said, we use this rho to compute a K. That's it for me. So in this project, we use circulant embedding for sampling from the random field, but we could equally look at different sampling approaches, for example, the SPD-based approach or the wavelet representation approach, and see if we can extend the smoothing to those methods. And the other thing is that instead of looking at this linear elliptic PDE, we could look at different types of PDEs where maybe correlation between the levels is not so easy to establish. Thank you.
Any burning questions? No. Okay. Thank you again.